In this module, we will consider static and kinetic friction. When two surfaces are in contact, a force acts between them that resists relative motion. This force depends on several microscopic effects, and experts still do not all agree on a universal microscopic description of the effect. But the concepts of static and kinetic friction provide a very useful macroscopic description of the effect. Static friction is a force that acts to keep two surfaces from moving relative to each other. And kinetic friction is a force that acts to decelerate two surfaces that are moving relative to each other. The magnitude of the static and kinetic frictional forces are defined to be proportional to the normal force acting between the two surfaces experiencing the frictional force. That is, if you have two surfaces pressed against each other, the harder they are pressed against each other, the greater the frictional force. Static friction is defined by the equation that the magnitude of the static friction is less than or equal to the coefficient of static friction, mu sub s, times the magnitude of the normal force. Now, the static frictional force is very similar to the normal force in that the static frictional force provides only enough force to keep the acceleration of the object zero. Remember, it's static friction. The two objects are not moving relative to each other. They have zero acceleration. And you only need as much force from static friction to keep the object from moving as you are pushing against the object with. But there is a well-defined maximum static frictional force that can be delivered. And that is demonstrated by the equation which says that the frictional force must be less than or equal to this quantity, which is the coefficient of static friction times the normal force. So we could have very small amount of force up to this maximum amount of force, which is mu sub s times n. The kinetic frictional force is governed by the equation that the magnitude of the kinetic friction is equal to the coefficient of kinetic friction times the normal force. And basically, by the very definition of what you mean by static and kinetic, the coefficient of static friction must be greater than or equal to the coefficient of kinetic friction. Now, the direction of both static and kinetic friction is parallel to the surfaces creating the friction, that is perpendicular to the normal force that is, at least in part, responsible for the friction. Let's first of all consider kinetic friction. The direction of the force is in the opposite direction of the velocity. So, if the object is moving with a velocity towards the right, then kinetic friction will produce a force acting towards the left, trying to slow the object down. The magnitude of this force we can write as little f sub k, and it's equal to the coefficient of kinetic friction times the magnitude of the normal force. Now, when we are writing out Newton's laws of motion, we can use either f sub k, or we can expand it in terms of the normal force and the coefficient of kinetic friction. We can write out either one of these in the equations as long as the velocity of the object is not zero. Now, this may seem a little bit unusual to state this at this point, but there's a reason for this, which we'll see when we consider static friction. The direction of the frictional force in this case is opposite to the direction of the net non-frictional forces acting on the object. So if we push from the left toward the right with a force, let's call it F sub parallel, where parallel means these are the forces which are parallel to the surface, perpendicular to the normal direction of the surface. In this case, the force of static friction will act towards the left to oppose this, so that the sum of the non-frictional forces and the frictional forces will add up to be zero. Now, when we are writing out Newton's laws of motion in the situation of static friction, we want to only use the magnitude of the static frictional force when writing out these equations. We never want to substitute in at this point that it's related to the coefficient of static friction and the normal force. Why is that? Well, remember what the equation says. It says that the magnitude of the static force is less than or equal to mu sub s n. Now, we know that the object is supposed to remain constant, but if we push on the object with very little force towards the right, a small value for the magnitude of F sub parallel. But we use the maximum amount of frictional force that we could get, mu sub S times N, then this is probably going to be larger in magnitude than our F parallel. And the sum of those forces would not be zero. And we would have the contradiction where we're saying that there's a net force acting on this object, but we're saying that it is having no acceleration. We have used a test in place of an equality, and this is just not the proper thing to do. But it's a mistake that students often make. So let's try not to do that. To look at this more carefully, let's consider friction on an inclined plane. So we have the mass on the incline, we have the force of gravity acting down, the normal force acting up, and we're going to assume that the force of friction is acting up the plane, whether it's kinetic friction or static friction. Essentially, we're going to assume that the block, if it's in motion, has a velocity which is down the incline. We can draw the free body diagram for this object. So we have the force of gravity, the normal force, and the frictional forces, whichever one we're using. And in this case, it makes sense to orient our coordinate systems and our unit vectors to be parallel and perpendicular to the incline so that we can decompose the force of gravity in this case. And we can write out, for example, that the normal force is the magnitude of the normal force times the j hat vector. The acceleration vector is all parallel to the incline, so it's the magnitude of a times the I hat unit vector. And the force of gravity is going to be mg times sine theta times the I hat vector minus cosine theta times the j hat vector. And of course, the two different kinds of friction will both be acting in the I hat direction, actually the minus I hat direction up the incline. So when considering kinetic friction, we have minus F sub k I hat, or we can also write it as minus the coefficient of kinetic friction times the normal force times I hat. But if we're considering static friction, we only want to write it as minus F sub s times I hat. All right, if we consider the components of the forces and the acceleration acting in the j hat direction, then what we find is the equation that n minus mg cosine theta is equal to 0. This tells us immediately what the normal force is in terms of the angle of the incline and the gravitational force and the mass. If we consider the case when the velocity is equal to 0 and remains so that we are in the situation where static friction applies, then what we get for the equations of motion along the incline is that minus the magnitude of the static friction plus mg sine theta is equal to 0 because we're assuming the object is not accelerating, it's static. So this tells us that the static frictional force needed to make this so is mg sine theta. We can now test to see if this is actually possible. So we use now the equation relating the static friction to the normal force and write this out. So the static friction we can write out as mg sine theta. We know that this is less than or equal to the coefficient of static friction times the normal force, and we can expand out what the normal force is. So this means that if we eliminate mass times gravity from both sides and bring the cosine theta to the left-hand side, this is telling us that the tangent of theta must be less than or equal to the coefficient of static friction. So what this is saying is that if tangent of theta is less than or equal to the coefficient of static friction, then the block will remain at rest. But if tangent theta happens to be larger than this coefficient of static friction, then static friction cannot hold the object in place and it will slide down the inclined plane. Now, if you stop and think about this physically, if theta is very, very small, then the normal force will be large, the frictional force will be large, and the component of the acceleration of gravity along or parallel to the incline will be very small. So for small angles, frictional forces are going to be large enough to hold the block in place. But as we increase the angle, the normal force is going to decrease, the force of gravity pulling it down is going to increase, and eventually there will be an angle large enough where the coefficient of static friction will not be large enough to keep the mass in place, and it will start to slide. Now let's consider the case where either we're at that or beyond that angle where static friction can hold the mass in place, or we have a non-vanishing velocity down the plane. And of course, we have assumed that the velocity is going down the plane in the direction of positive I hat when we have written out the force of kinetic friction to be in the opposite direction. We can consider the case where the block moves up the plane as long as we switch the direction of the force of kinetic friction. So, assuming that the velocity is down the plane, the equations of motion in the I hat direction give us that minus the magnitude of the kinetic friction plus mg sine theta is equal to mass times acceleration of the object. And we can expand out what the force of kinetic friction is in terms of the coefficient of kinetic friction and the normal force, and simplify this by dividing out the mass, and we find that the acceleration is equal to g times the quantity sine theta minus the coefficient of kinetic friction times cosine theta. Now, the block will accelerate down the incline, given our choice of the directions of I hat and j hat, if a is greater than 0. But if a happens to be less than 0, then the acceleration will be negative, and it will be decelerating as it moves down the incline, that is, slowing down. So, depending on whether the force of gravity acting along the incline is greater than or less than the force of kinetic friction acting up, the object will either speed up or slow down as it moves down the incline.